process.
Okay, so I sent an announcement along the back of the link. But you know, but some are complaining that the video quality isn't good. I can't do much. So you're trying to keep it closer to the.
It's like different.
So don't delay on that. It's right. Okay. It's just a good aim.
Yeah.
It's nice to hear you. Yeah.
Yeah. Oh, you do? Yeah. Yeah, actually, because like it's a friendly, so it's not like not as and it was actually. But that is very typical. It's not uncommon. Sure. Yep.
think we should start. Good afternoon. So before the class, I maybe have noticed in the announcement some students asked me whether can some third-party libraries such as sklearn can be used to finish the cross-validation. And my answer is unfortunately no. Although it's very fabulous, great job for you guys to find out such kind of third-party libraries, and very probably in your future adventure in machine learning and data science, you will depend on those kind of APIs or libraries. But in our specific class, you are required to understand the process of cross-validation. That means you need to implement the logic by yourself. Right? But after that, you can use you can choose whatever packages you like to do your cross-validation. But in this specific homework assignments, you have to do it by yourself. And also, you need to submit your code. That means our TAs will check your logic. So don't just call one line of other people's function to do that. Okay, so let us continue the gradient descent. So in the last lecture, we have introduced several important basic concepts, such as local maximums and local minimums, and global maximum and global minimum. These concepts are quite intuitive. And then we introduce a class of very important functions called convex functions. And actually, to memorize what is a convex function, I think you need to memorize a convex inequality, right? So basically, a convex function, if we say a function f is a convex function, say it's from a mapping from the d-dimensional input to some real value, right? And we need to ensure that the function value of the convex combination of arbitrary two inputs. So here, the convex combination of two inputs, which is lambda alpha plus 1 minus lambda beta. And here, lambda should belongs to 0 and 1. This is a function value over the convex combination of two inputs, alpha and beta. This should be what? Align. Yeah, it's a line. Yeah, I mean, what's the remaining part of this inequality? Any impression?
Less than lambda f of alpha plus 1 minus alpha times f beta.
Yeah, exactly, right? So to describe it in a natural language, it just means, okay, the convex combination, the function value over a convex combination is no bigger than the convex combination of function values. So basically, that means the right-hand side will be lambda times the function value, right, at alpha plus 1 minus lambda times the function value at beta. So if a function satisfies this convex inequality at arbitrary two inputs, then this function is called a convex function. And also give us some visualization of a convex function, right? So basically, you can draw a quadratic function, which is a typical convex function, and you can randomly pick up like two inputs here, and here is x-axis, right? It's alpha and beta, right? And function value at so here is the as we mentioned before, right? The convex combination of two inputs should be staying on the segment which connects alpha and beta, right? So it should be here. And the position depends on how you choose the coefficient lambda, right? And the function value the convex combination is here. It's here. And then we can check the convex combination of function values. So how can we do that? We can draw a line, right? We can draw a line which connects the two function values, right? And then you just draw a perpendicular line which crosses the convex combination of the inputs. And you cross this line, you end up with the convex combination of function values. And you just compare the two values, right? So obviously, the convex combination of function values is bigger than, is higher, right, than the function of the convex combination of the inputs. So this is a typical example of convex functions. And a very important concept, and a very important property of the convex combination is what? So convex functions have many cool properties, but the most important property you should keep it in mind is that as long as your convex function has a local minimum, what does it mean? What does it imply?
It's the global minimum.
Yeah, it is global minimum. Or in other words, all the local minimums overlap, and we have only one global minimum. But you also need to keep in mind there could be some exceptions that the function is unbounded. That means there could be no local minimums, no global minimums. A typical example is a line, right? It corresponds to our linear regression function, right? The line, you don't have a local minimum nor local maximum. So after we introduced those basic concepts in optimization, we discussed what's the general strategy for us to minimize a target function. So what is the general strategy? So let me write down. This is our target function. This is our target function. And I assume it's a mapping from a d-dimensional space to a real value domain, right? So now we want to minimize this function. What's the general strategy can we use? What's the general idea? So let me write it down more formally. So we want to maximize this function. We want to find some local minimum. If it is a convex function, then bingo, we are also, when we find out the local minimum, we end up with global minimum as well. Right? But the question is, how can we achieve this goal? How can we do that? Any idea? Can you guess?
Gradient descent.
Yeah, gradient descent. So what is the detail for gradient descent? This is the topic of this title is gradient descent, right? What's the detail of gradient descent?
The next position is equal to the previous position, plus or minus your step size times the gradient.
Yeah, exactly, right? So basically, we use some step-by-step approaches, right? We start with some initial position. So you can imagine in the d-dimensional input space, we start with the initial position. Say we indicated, we denoted by alpha0, right? And then we use some strategy to continuously move the position of input. Say alpha1, alpha2, alpha3, continue, right? And we just need to guarantee that after each adjustment of the location, our function value decreases. And finally, we expect that we can end up with a local minimum, or at least some location very close to local minimum. This is our general strategy. It's called algorithmic steps. And then the question is, how can we determine the direction and the step size to adjust our location? Right? As this gentleman just mentioned, we can choose which direction. Which direction we can choose?
Decreasing.
Yeah, decreasing. Of course, it's decreasing directions. Or specific direction. Yeah, he just mentioned. Can anyone repeat what he said? Okay, let me repeat. So we can use the opposite direction of the gradient. So basically, the general moving procedure is defined as follows, right? So suppose right now we are at the location alpha k, right? And then to move alpha k to alpha k plus 1, we just move toward the opposite direction of the gradient at alpha k. So the gradient of alpha k we can denote it by here, right? Nabla. And because this is a opposite direction, so we multiply it with a minus sign, right? And then we then multiply with a step size. Say we denote it by gamma k, and we add it to the current location. And then we end up with our new location, alpha k plus 1. So this is called gradient descent step. So now we can move minus sign outside, right? Because we do not need this plus. So it's we can simply use minus here and then times step size in front of the gradient. So this is a gradient descent step. The question is why performing gradient descent can increase the function. We have explained it intuitively at the end of last lecture, right? So can anyone help us review the reason? An idea?
Question, because we're finding our max instead of the minimum?
No, we're trying to minimize the function. Oh, sorry, it's minimize. It's minimize. So to explain this, the reason, the rationality of this strategy, we can start with visualization, right? So suppose our function looks like this, right? This is function curve, and this is our x-axis because for simplicity, we assume we are in a one-dimensional input space, right? And suppose this is our current location, say alpha k. We can check. We can check what's the consequence if we move alpha k toward the direction of the gradient. Right? So the gradient is actually the slope of the tangent line of this function curve at alpha k. Right? And by looking at this tangent line, we can see that its slope is positive because the angle between this line and the x-axis is less than 90 degrees. Right? So if we update our input alpha k toward the direction of the gradient, we're actually adding a gradient because the gradient is positive. We're actually adding a gradient, meaning that we move alpha k along the right direction. Right? And then we can check what happened if I move alpha k, say, to this place. And then what happened to the function value? The function value is increased, right? And someone may question that this is some kind of coincidence, right? So we can take a look at another example. So suppose our function is not monotonically increasing, right? We're decreasing. And then we can check again whether what happens if we move our input location toward the gradient direction. Right? So here is our starting point, right? So this is x-axis. So again, we need to first check the gradient. So the gradient again is the slope of the tangent line for the function curve, right? At this specific point. So now, what's the slope? What about the slope?
It's negative.
Yeah, slope is negative, right? Because the angle between the line and the x-axis is bigger than pi over 2. Right? So the gradient is actually negative. So now, if we update our input toward the direction of gradient, we're actually moving along the left direction, right? Because the gradient is negative. Right? We're actually subtracting the original location by some amount. Right? And then suppose we are now at this position. Then what happened to the function value? This is the original function value. This is a function value after we update our input according to the gradient direction. We still get increased function value, right? So now we can see actually gradient descent, a gradient direction is a direction that increases the function.
So gamma k is your step size, right?
Yeah.
So do you update, because of the k, I'm assuming you update on each step, the step size?
Yeah, that's a very good question. We are going to discuss how to choose the step size later.
All right.
But now we need to first ensure that we're choosing the right direction to update our function, function inputs. Right? So from those intuitive examples, we can say actually the gradient is the direction to increase function values. Now that we want to minimize the function, we can choose the opposite direction of the gradient. That's where our gradient descent strategy comes from. And next, we need to give some rigorous analysis. Because this is just some case study, right? And the real functions could be very complex, right? It's not monotonically decreasing or monotonically increasing. And then we should give a more rigorous analysis to understand why gradient descent strategy works. So now let us try to analyze this problem. So suppose our starting point is alpha, some point in the d-dimensional input space. Right? And we can move alpha toward any direction in the d-dimensional space. Right? Let us try to investigate what kind of change of the function values after we move alpha from some arbitrary direction. So we denote this direction by a unit vector u. So what is unit vector?
Size 1.
What?
Size 1.
Yeah. The norm of the unit vector should be 1, right? If you still remember the definition of norm. and then the vector only indicates the direction information. So if we update our input location towards the direction indicated by u along some step size h, then after the updates, our location becomes alpha plus h times the unit vector u, right? No question at this point, right?
That's just our next gradient descent step. Is that what that is?
I'm not saying this is a gradient descent step. I'm just assuming you're moving the input location toward arbitrary direction in the d-dimensional space. And then we'll look into what kind of direction can ensure the decrease of function value. Right? So here to emphasize, these are all vectors. I add an arrow on top of those letters. So this is updates after we move the input location toward the direction indicated by u along step size h. So the question is, when we evaluate the function at this new location, is it smaller or bigger than the function value at the original location? Right? So it is bigger or smaller. This is something we need to analyze. Then how can we compare the difference of the function values in terms of their locations? Any idea?
Sum of error squared?
What?
Sorry, do you do like error squared?
Not yet. Here we just want to compare which one is larger, right? If we can choose some specific direction u to ensure that this function value is smaller than this one, then u is maybe a good direction for us to update our location, right? But the question is that how can we analyze the difference between the two function values? Any idea?
Convex inequality?
What?
Using the convex inequality. So the inequality.
No, right now we haven't assumed any.
Okay, you're not under.
Yeah, I'm not assuming there is a convex function.
You just compute the output of both, right? And compare.
Yeah, of course, we can compute the outputs if we know the function form. But right now, we want to give some analytical results for general functions. Right? We do not assume the function form is deterministic, is specific. Right? We just assume the function is differentiable. Right? Any idea? So actually, if we can try to remember what we have learned in our calculus course, this is the right way to apply a classical formula called Taylor expansion. So what is the general form of Taylor expansion? So given a function at some specific location, say fy, right? So we want to expand the function at some specific location x. How can we do that? So it is equal to fx plus what? Come on, we can try to review it together, right? So the first order term is the gradient at x transpose the difference between the two inputs, right? Y minus x. This is also the inner product, right? Y minus x. And then plus the second order term, right? The third order term, fourth order term, that's actually an infinite number of terms. But here, we are enough to use the first two terms. So the remaining terms can be written as a higher order term of the norm of the input difference. So what does higher order term mean?
It's an error.
Yeah, it's error. Right. So what's the property of this error? This is small, it's not big O, it's small. So it means that when x approaches y, the limit of this higher order term over the norm of y minus x is approaching to 0. So if you want to express it, to explain it in natural language, it just means, okay, when x is closer and closer to y, the value of this higher order term is much smaller and smaller as compared with the norm. Meaning that when it is enough, when y is enough close to x, we can just ignore the value of this higher order term. And then the whole function value is totally determined by the first two terms. That's actually consistent with our understanding of the gradient, right? So no matter how complex your function is, right, at very small local region, you can just use the tangent line to approximate your original function. But this only holds when these two segments of the inputs are enough small. Right? This is actually directly justified by the Taylor expansion, because when y and x are enough close, the value of the higher terms can be ignored, and the function value is determined by the first two terms. Actually, the first two terms defines a linear function of x. Okay. So now we can use Taylor expansion to compare the two function values, right? So here, the updated location can be considered as y here, right? And the original input location can be considered as x. And we can expand the function value at y using x. Right? So just substitute the x and y for the two new locations. Just simply apply it. Right? So what can we get? We can obtain that the Taylor expansion of alpha plus h times the unit vector u is the function value at alpha, and plus the gradient at alpha, right? Transpose and multiplying with the difference between the two inputs. The difference is actually the small step size we move, right? Times h multiplying with the unit vector, and then plus a higher order term of the norm for the difference, right? So the difference actually is h times the unit vector u. So remember here the u is unit vector. Then what's the value of the norm? H times u. It's just h, right? And here we assume h is positive. Why we assume h is positive? If h is negative, you're actually not moving toward u. You're moving the opposite direction of u, right? So for consistency, we just assume h is bigger than 0, right? So here the higher order term is actually a higher order term of h. That means that when h is approaches to 0, this higher order term of h over h is 0. Right? So when h is enough small, you can just ignore the skew of this higher order term. So now let us assume the case that h is enough small. Then the function value at the new location is totally determined by the first two terms here, right? And then when our function value after the updates will be decreased.
The second term's negative.
Yeah, obvious, right? This is the original function value. This is the function value after the updates. Then this is their difference, right? Of course, you have to assume the step size is enough small so that this other term is ignorable, right? So then the mailing term which determines whether your function gets increased or decreased is the second term. Right? And what is second term? The second term is simply you can move h outside because it's just step size, right? And then it becomes h times the inner product between the gradient at alpha and our direction u, right? So to ensure this term is negative, we need to ensure the inner product is negative, right? So as long as we can move a direction such that its inner product with the gradient is negative, we'll guarantee the function value to be decreased as long as h is enough small. Right? Then the next question is that how can we choose the direction u to make the function decrease to be as big as possible? Any idea? How to choose the direction, update direction u to make a function decrease biggest. Do you have any choice of u?
Do some type of like probing where you're randomly picking u and then adjusting it based off.
Yeah, that's one idea. This is more practical ideas. Now, what if I want you to give a direct answer, a rigorous answer for that?
Find the gradient.
Yeah, that's the right direction. Can it be more explicit? Yeah, we can do analysis, right? So we know that this term, the value or the amount of this term is totally determined by this inner product, right? So suppose this is the direction of the gradient, right? And this is the direction of the u. And then the inner product actually the projection, right? If you project your gradient toward the direction indicated by u, the projection length is actually the amount of decrease here, right? Then the question is that along which direction you end up with the maximum projection length?
The same direction as the gradient.
Yeah, the same direction, right? Obviously, because if you are not same direction, you want to compute the projection length, you have to multiply the length of the original gradient with this cosine angle, right? And because we want to do the decrease of function value, of course we cannot make u to be the same direction as the gradient. We have to use the opposite direction, right, to ensure the inner product is negative. But we need to ensure the completely opposite direction of the gradient. So we can choose u to be a negative direction of the gradient. And because u is a unit vector, we should normalize the gradient by its norm. So this is optimal direction to decrease our function, because if you update your input location along this direction, you can ensure the smallest, the largest function decrease. So this direction is also called steepest descent direction. And if you use a negative gradient direction to implement your gradient descent algorithm, it is called steepest gradient descent. But does steepest gradient descent really mean a good optimization algorithm? The answer is actually no. So the steepest descent, the steepest gradient is optimal only in these small steps, in this small step. Or in other words, you can consider it is locally optimal, because we only focus on this particular step, particular location. And if we found that if we update the direction along the negative gradient, we get the maximum function decrease in this local region. But that does not necessarily mean globally, or on average, if you keep using this kind of strategy, you have the best efficiency or speed to reach the final local minimum. That's kind of, there's an analogy like a greedy algorithm and the global algorithm, right? So steepest gradient descent is more like a gradient algorithm. Every time we choose the optimal decision according to current situation, this is kind of a gradient strategy. But it does not necessarily mean that when we combine all of those gradient strategies together, we end up with the global optimal strategy. But anyway, in our class, we are only focused on the steepest gradient descent. And in the future, your future exploration or adventures in optimization for machine learning or data science, you will have a chance to learn various different types of gradient-based optimization algorithms. And they have different convergence rate and the speed and etc. So now we have explained why we should choose a negative gradient direction to update our location and to decrease our function. And here, let me write down the general gradient descent framework, algorithmic framework. It's very simple, but most machine learning and data mining algorithms, the training algorithm are some kind of variant of this framework. This is our algorithm for gradient descent. To run our gradient descent, we need to know our target function, and also we need to indicate a starting point. Any questions? Okay. So first, we initialize our location to be our start. Then we do a loop to continuously update our input locations. So we denote the after k step, our function input is alpha k, and alpha k is obtained by update the last location alpha k minus 1 toward the negative gradient direction, and multiplying with a step size gamma k. And we continue this process until the norm of the norm of the gradient at current location is smaller than some specific tolerance level, or the maximum number of updates is reached. Here specified by t. So usually you can set tau to be quite small, like you can set it to be like 10 to minus 3 or 10 to minus 6. It depends on your applications, your need for applications, and also why you set up a maximum number of updates, because this is kind of a trade-off between your computational resources and the requirement for the accuracy, right? Because it's not obligatory. Actually, in practice, it's not obligatory for you to find the exact local minimum. In most of the time, as long as your result is close enough to the local minimum, that's okay. So that's why you can freely set up the tolerance level and also the number of maximum updates. So this is a general gradient descent framework. Any questions so far?
So that's a z less than or equal to z or t. Is that what that says?
Oh yeah, you need to give the algorithm also these two hyperparameters.
Okay.
So as long as you can imagine this is a function, right? It's your implemented function, and when you call the function, you need to specify the tolerance level tau and maximum number of updates, and also you need to give the initial position. Any questions so far?
What would be a strategy that changes step size?
Yeah, that's a very good question. That's something we need to discuss right now. Other than that, are there any other questions in understanding this framework? Yes, it's straightforward. You need to be able to implement your own algorithm following this framework. If you have taken a look at the homework 3, you are required to implement that.
I have a question actually. So the alpha k equals alpha k minus 1?
Yes.
That seems different than what we were talking about, because it seemed to me that we were always going alpha k plus 1 instead of alpha k minus 1.
Oh, it doesn't matter. Right?
Oh, okay.
It doesn't matter at all. You can replace alpha k minus 1 by k, and then k is changed to k plus 1.
Okay.
It doesn't change. It doesn't have any change in the meaning of this algorithm. Right? If you don't like it, I can replace k by k plus 1. Now in the final check, you need to check the gradient of r at alpha k plus 1.
Okay, that's okay. You don't have to.
Okay. So now the remaining question would be, how can we identify appropriate step size? Right? So from our previous analysis, we know that in what kind of situation we can guarantee the gradient descent decrease the function. There's a key assumption. When we use a Taylor expansion for analysis, right? What's the key assumption?
H is small.
Yeah, exactly right. H must be small, meaning that H is actually the gamma k here, the step size. If step size is very large, then this Helder term is not ignorable. So when we use Taylor expansion for the analysis, we assume H is enough small such that this Helder term can be ignorable. The scale is very, very small. But if H is large, is significant, then the right-hand side of Taylor expansion is not only determined by the first two terms, it's also determined by this term as well. So to ensure after every update, our function value get decreased, we need to ensure the gamma k to be enough small. But the question is, what kind of gamma k is enough small? It's very hard to use Taylor expansion to determine this because this term is very, very complex. It's hard for us to evaluate. Then what can we find out the appropriate step size. So here we'll just briefly introduce some theoretical results. And unfortunately, those theoretical results cannot give you the practical guidance to choose gamma k as well. But I just want you to have a sense of that. And we'll omit the proof because those proofs are not difficult, but it's quite tedious. It's not covered in this class. But in the future, if you take some optimization class, you will learn how to prove the convergence guarantee and convergence weight. So a commonly used assumption to derive the valid range of step size is called Lipschitz assumption. So I'm pretty much sure you guys have heard about this definition before in calculus course, but until yesterday, I cannot remember what is Lipschitz condition as well. So let us review them together, right? So what is Lipschitz continuous? So we say a function, and here the function could be a multi-output functions. Right? It doesn't necessarily to be a scalar function. So suppose this function is mapping from a d-dimensional space to a k-dimensional space. And we call this function g is L Lipschitz. If for any two inputs in the domain, we have the norm of the function difference. I mean, it's a norm of GP minus GQ is upper bounded by the norm of the input difference multiplied with a factor L. This is called L Lipschitz. This is a very commonly used assumption in proving the optimization, all kinds of properties in optimization algorithms. So any question in understanding this Lipschitz continuous definition?
What's L? Is that a constant?
Yeah, L is a constant. So if L is 0.1, we can say, okay, it's 0.1 Lipschitz continuous. If L is 1, we can say it's 1 Lipschitz continuous. It's just a constant L. But if this inequality holds for arbitrary two inputs for some specific constant L, then we call this function is L Lipschitz.
This is lower better.
You mean L is smaller better? Yeah, for gradient descent optimization, yeah, the smaller better. We'll explain later, right? And for other, I don't know. But this condition is very widely used as some precondition to prove the optimization algorithms. So nearly, I cannot find out any algorithm that does not use this Lipschitz continuous to prove the convergence of the algorithm. But later, why these are important, you will learn them from the advanced optimization class. But here, let me drop you the conclusion. If the gradient of our target function is L Lipschitz continuous, and we choose our step size. But here we assume we're using constant step size, meaning that for each step, our step size is the same. If we choose our step size to be less than or equal to 1 over L, then the gradient descent framework, as we just mentioned, is guaranteed to converge. And convergence rate is bounded by 1 over epsilon. Here epsilon is some error. So this is the first result. Oh, and the rate is to achieve such kind of rate, we need to assume the f is a convex function. Sorry, I need to. And further, if f is convex, the convergence rate is big O 1 over epsilon. So first, let us look at the first conclusion. So if we can choose the step size to be below 1 over L, then we can guarantee the gradient descent, as we just mentioned, converges to some local minimum. No question at this point, right? It's just some condition, but it is built on the condition that your gradient must be L Lipschitz, meaning that for arbitrary 2 inputs, right, your gradient at these 2 inputs, their difference norm is bounded by L times the difference, the norm of the input difference. And then, if we can choose lambda to be sufficient small, meaning that it be less than or equal to 1 over L, then our gradient descent is guaranteed to converge. And then the following question would be how fast it will converge. Right? And there is some general conclusion for general gradient descent, but here we just list the convex function, meaning that if the function f is convex, then the convergence rate is big O 1 over epsilon. So here we need to understand why. What does it mean? So epsilon means that some pre-specified level that we want to, after k updates, our function value is close to the function value at the local minimum. Their difference is smaller than or equal to epsilon. So this is some pre-specified error level epsilon. Then to reach this second conclusion tells us that to reach this error level epsilon, the number of updates is big O 1 over epsilon. So what does big O mean?
Upper bound.
Yeah, it's upper bound, right? It comes from the data structure course, right? So basically it means that the number of updates k is upper bounded by some constant m times 1 over epsilon. Any questions so far?
So epsilon is like an error.
Yeah. You just want to know. For example, I want to know. Okay, I want my function value to be as close as to the value as some function minimum. Their difference is only like 0.001. And then I want to know how many updates I should do to reach such kind of accuracy. Okay? And then we know that the number of updates we need is 1 over 0.001 times some constant m. Okay. So at least multiple thousands of updates.
So m is like some constant. How do we determine what m is?
How do you determine m?
Yeah.
Well, to determine m, you need to know how to prove this.
Okay.
It's a very elegant but lengthy proof for this. If you're interested, you can check the extra resources in our cost web page. And yeah,
So what does M stand for though? Just that it's like a multiplier.
it's not multiplied. It's much more complex than the constant. But it is some constant which describes the properties of f. So it's actually related to the characteristics of f.
Okay.
But here we just ignore it. Any other questions up to this point?
So if you want a smaller error, you want a lot more updates and a smaller step size?
First,
from the
if you want a small error
Yeah.
from this result for convergence rate, we know you must need much more updates, right? Because it is 1 over the error. Right? If you want like 10 to minus 6, then it have at least a million updates, right? If you only need 0.01, maybe 100 or 200 updates will be enough. This is some direct conclusion. But if you want to know how to choose the step size, it actually determines by here, right? And that actually connects the question you just asked. You're saying whether the smaller L the better. Right? So now we can say the smaller L the better. Because the smaller L means that the range of the step size is larger, right? Because upper bound is 1 over L. Then the larger the step size, the larger movement you can make in your gradient descent. But unfortunately, it is very hard for us to identify L, even your gradient is L Lipschitz. Okay, so this is just for a general convex function. But if our convex function belongs to a special family, we can have an even better convergence rate. Why we should be interested in this special type of functions? Because they are related to many machine learning objectives, like SSE. We intensively discussed in previous lectures. Are just one type of such kind of convex function. So this convex function is called a strongly convex function. So we say a function f is eta strongly convex if here eta is positive. If for arbitrary two inputs alpha and p in a d-dimensional space, it satisfies the function value at p is no less than the function value at alpha plus the inner product between the gradient and the difference between the inputs, then plus a quadratic term. So if you check the cost material, there's a typo in the cost material. The cost material actually make a wrong direction of the inequality. So be careful. It must be bigger than or equal to. So this is called a strongly convex function. So what does it mean? Why is it called strongly convex function? So this is just the mathematical definition, right? So we can take a look at the visualization. So actually, strongly convex function provides us a tighter bound of your convex function. So the first two terms are the first order Taylor expansion, right? This is Fp and this is alpha. And this is actually inner product between the gradient and alpha and difference between P and alpha. And then we plus a second order term, right? So if you expand your Taylor expansion in the second order, that will correspond to what? that corresponds to a quadratic form, right? So if you expand Fp and F alpha with second order Taylor expansion, it will be like this. And second order will be P minus alpha transpose. What? The second derivative, right? Second derivative at some phase theta is not exactly alpha, and P minus alpha. So this is also a quadratic term. And strongly, if we do the exact Taylor expansion, if you feel unfamiliar with this, just go back and check your calculus book. This is exact expansion, Taylor expansion for second order Taylor expansion. So the third term will be a quadratic form, and inside this quadratic form, the matrix here is the second derivative at some specific location, and usually it's very hard to determine this location. And here, strongly convex, just saying that we can lower bound our function value by another quadratic term determined by eta. So what's the geometric meaning for that? What's the visualization for that? Imagine we have a convex function here.
Sorry, what's the order of that statement? So if the function is strongly convex, then that holds. Does it hold the other way around? Is it an if and only if statement?
No, we are saying actually if these conditions are satisfied, we can call the function f is eta strongly convex.
Okay.
That's the definition
That's
for
the
strong.
definition of
Yeah, yeah.
strong
This definition of strongly convex. F is convex, and also all the function value of f satisfy these inequalities, and is lower bounded by the first order Taylor expansion plus a quadratic term. It calls strongly convex.
Okay.
Right. So suppose this is a strongly convex function. So what does strongly convex provide us? So you can imagine that for any convex function, it can be lower bounded by its first order Taylor expansion. That is the tangent line, right? So you can draw a tangent line at any input location. You will find the whole function, whole convex function is lower bounded by this tangent line. You can try that. But now, strongly convex provides you an even better bound, an even tighter bound. Why? Because in addition to this tangent line, which is the first order Taylor expansion here, we add a second order term. We add a quadratic term. So it actually represents a quadratic function. If we draw it in visualization, it ends up with a quadratic function. This is our tangent line, right? And the strongly convex function has a lower bound, which is the tangent line plus a quadratic term, which is quadratic function. So actually, here's the quadratic function. So now, let's compare with the common convex function. Strongly convex function has a tighter lower bound, right? Any questions? This is just from the visualization point of view to give you an intuition why it's called strongly convex, because it has a better lower bound. And if the gradient of your function f also satisfies Lec-15, you can derive that the function is also upper bounded by a quadratic function. That means the function is sandwiched between two quadratic functions. One is from the definition of strongly convex, the other is from the Lec-15. So this can be proved from the calculus knowledge, but we won't go through this proof. It just to give you a intuitive sense for that. And you can say this is actually a special type of convex function. And then if your function, your target function is convex function, it's a strongly convex function. And then if you choose your step size to be less than or equal to 2 over eta plus L, then your gradient descent guarantees to converge. And now, the fabulous point is that the convergence rate is a big O logarithm 1 over epsilon. That's the result. That's a benefit of a strongly convex function. As we just mentioned, right? If it is just a common convex function, it's not strongly convex. We can always say, oh, the convergence rate is 1 over epsilon, right? But now, if it is strongly convex, if we choose the step size to satisfy this condition, then we can guarantee that convergence rate is logarithm over 1 over the error. Then now you can imagine if you choose the same tolerance level, the same error level, say 10 to minus 6. So you can say if you use if your target function is just a common convex function, then you have to use at least millions of updates, right? But now, if your target function is strongly convex, your number of updates will be logarithm of 10 to minus 6. It will be much smaller. And actually, many commonly used objective function is strongly convex, including the SSE, as we just mentioned.
So are we gonna have to determine if something is strongly convex or if it's also or if it has an L Lipschitz? Oh, I see.
You mean homework assignments or in the general?
Yeah.
No. It just give you some theoretical sense of that. You're not required to.
For gamma inequality, is that an alpha on the right hand side? At the top of the right hand side, is that alpha?
2. It's 2. Just 2. So imagine if I do not, this is a strongly convex. Okay, we require gamma is less than or equal to 1 over L, right? But right now we know it's the eta strongly convex, and now we choose gamma to be less than or equal to 2 over eta plus L, right? So you can, if you move 2 in the denominator, it's actually 1 over the average of eta and L. Right? It's actually some consistency here. Actually, there's some. The proof is also has some analogy. So, any questions so far about understanding the convergence rate in those?
When he asked you about how do you tell if it's strongly convex again? That sentence.
Following the definition, yeah.
It's when it's greater than 0, or how do I read that?
How to what?
How do I read that?
How to what?
How do I read it?
How to read it?
Like the definition of a strongly convex function?
Yeah, if the function f is strongly convex, it means that for any 2 inputs alpha and p, this inequality holds.
Oh.
And the eta here, which determines the lower bound, is called eta strongly convex.
Okay.
Any other worries about understanding this definition?
And SSE is strongly convex.
Yes.
And
SSE is for a linear regression model, strongly convex. I'll leave it as a practice for your homework.
is it also does also have the L Lipschitz?
Yeah, of course. Actually, many mean square error or sum of square error functions you can prove that if you arrange them into the matrix and vector forms, you will see that they are both ellipses and strongly convex. You can prove that. That's why we need to know the fancy properties of strongly convex functions. So in practice, these are just giving you some properties, some theoretical analysis about how to choose a valid step size, right? But in practice, people cannot identify what is L and what is eta. So practically, there are several other methods to identify eta algorithmically. And here we don't have time to go through these detailed steps, and they are briefly covering cost material, but you are not required to master them, don't worry. In your implementation of gradient descent, you just try to blindly tune the gamma. But you need to know that there are several commonly used approaches to automatically adjust the step size for each step. Those methods include line search, include backtracking line search, and all those methods have a rigorous theoretical guarantee that they will ensure your gradient descent using those strategies converge, and also the analysis for convergence rate. But those proof is not trivial. It's not trivial at all, and it's also quite lengthy. It's kind of properties of optimization research. To prove some properties, they have to write like two pages, 3 pages proof. It's quite tedious, but the knowledge they used is only restricted in calculus or some linear algebra. Oh, in the remaining about 6-7 minutes, I'll show you the implementation of the gradient descent, because you are required to implement some gradient descent in your homework. So I don't want it to feel difficult or confused. And this code are all shared in the course material. So I really hope you guys can copy the code in your Python IDE and play them. Okay. Can anyone see it clearly? Do I need to enlarge the text? Is it okay for everyone? Okay, good. So let me briefly introduce the logic of this implementation. So as usual, these few lines of code just import the necessary NumPy and Scipher libraries to implement our gradient descent, and also show out the plots. And then the following 2 lines actually is to evaluate our target function. And then our target function is just the 2-variable function, contains 2 variables x and y. And the mathematical form is in the course material. You can check that. And also we can derive an analytical derivative of the gradient, right? So it is implemented here. Because it's a df dx, right? It is df dy. It's a partial derivative with respect to x and y respectively, and finally we'll end up with a gradient vector. Because 2-dimensional inputs, we have a 2-dimensional vector, right? And then these several lines of code just show the contour line of your target function. So what is contour line? So contour line just simply means that your function is 2-dimensional, right? 2-dimensional. This is x and this is y. And contour line means that in a specific contour, all the function value at the inputs in this line are the same. That's contour line. And you are encouraged to study how these contour lines are plotted or generated. It's quite interesting. And then we are going to begin our gradient descent. This is our initial point. So we initialize our input to be 5 and 4, meaning x is 5 and y is 4. And also we perform a maximum number of updates is 10. It's very simple, right? Of course, you can try try more, like 100. And the values actually store all the function values in our updates, during our updates. And here alpha is our step size. And actually we try a various range of step size from a small, like 0.01 to very large, 0.75. And later we'll observe what kind of updating behaviors by using different step sizes to check whether this is consistent with our theory. And then the following 3 lines is just the gradient descent updates, right? We go through maximum number of updates, and for each update, update current input location to walk the opposite direction of the function gradient and multiply with the step size alpha, right? And then we store the current input locations in these arrays, values. And finally, we plot all the results. We plot the contour, we plot the updated inputs for each specific step size. So this is the basic logic of the code. Any questions so far? This is very straightforward. So you can download the code later and try to play. So now let us just run it and see what can we end up with. So actually, the plots we generated shows how the updated passes of gradient descent with different step sizes. So we can take a look at the first step size, which is pretty small, meaning that the step size is just 0.01. And those contour lines, those circles are actually contour lines, or this is just the contour lines, and indicating the function value is decreasing from the light colored contour lines to the dark contour lines, meaning that this is the local minimum. Any question? It's fine. And note these blue dots, those blue points actually represent the updated input locations by using our gradient descent. Remember, we perform 10 updates. So now, look at the first setting of step size, which is just 0.01. We see that the efficiency of the updates is quite low, right? So after 10 iterations, we're still quite far away from the local minimum, the local minimum scale. And we can check the final gradient. That means the norm of the gradient after the 10th updates here, right? Which is pretty big. So ideally, it should be as close as to 0, right? But right now, it's 5.76x, much larger than 0. So that means if you choose very, very small step size, then your efficiency of your gradient descent updates is quite low. And now let us try to increase the step size, right? Now we increase 0.01 to 0.01, enlarge for 10 times. So now we can observe. We can observe that our updates are much more efficient, right? So we start with the same initial point, right? At 4 and 5, at 5 and 4. So after 10 updates, by using step size 0.1, we get much closer to the local minimum, right? But there's still some distance, meaning that our choice of step size may not be sufficient good. And then we can keep increasing the step size, say to 0.2, we double the step size. And now we can say after 10 iterations, 10 updates, we get even closer to the local minimum. And we can change it, and to further revise it, we get 0.3 as our step size, we get even closer, even better. And this better or not result, the goodness of this result can be reflected by the norm of the gradient, final gradient, right? We can say the gradient, norm of gradients is decreasing. And we continue to increase the step size. We can say when we increase the step size to 0.5, we can almost say we have arrived at local minimum, right? It is from visually, visually we can see it is right at the center, right? And the gradient at the final step, the normal of the gradient is 0.03, almost 0. But what if we continue to increase the step size? We will increase the step size to 0.75. You can see what happened. Actually, your updates become much wilder, more crazy, such that your optimization path becomes zigzag. Although the final position is also close to the local minimum, but it's not as good as gamma being 0.5, right? Instead of being 0.5. Okay, this is just some simple examples. So I suggest you to download the code and play the code and also revise it to finish your homework. I will see you on Wednesday.